Here we're dealing with a basketball being dropped from 1.5 meters. It falls down, hits the ground, bounces back up. And we've got graphs of position in terms of vertical position, so height, changing as time passes, and also a graph of the velocity changing as time passes. And that's strictly the y component of velocity because it's not moving side to side anyway. And also we want to draw a graph of acceleration as time passes. First of all, let's examine the position and velocity graphs. How are position and velocity related in general? What's the relationship between those two quantities? Like, how do we define velocity in the first place? Yeah, velocity is the slope or the first derivative, the rate of change. Derivative of, in this case, we're going to say derivative of y with respect to time, because y is the variable we're using for position. So in terms of the physics, you'd interpret this as the rate of change in y. The change in y divided by change in time. So how much or how far the ball travels divided by how much time it takes. Or rather, how quickly that's changing at some instant. We're not really talking about like measuring how far it travels and measuring how much time it takes and dividing those. That would give you an average velocity. But we're talking about the instantaneous rate of change, how fast the height is changing as time passes right now, not over some period of time. And again, on the graph, that's going to represent, the derivative represents the slope of the graph, or more formally, the slope of the tangent line. Because if we're talking about, like, let's say at time 4, for instance, at instant 4, right over here, we're not talking about like the rate of change from some point on the graph to some other point on the graph. We're talking about the slope of the tangent line. The tangent line is going to be a line that's just barely skimming the graph, skimming the curve at that point. So what we care about is the slope of that tangent line. And the slope of that tangent line tells you the value of the velocity. And I really like having the graphs stacked vertically like this because that makes it really easy to compare a point on one graph and a point on the other graph. For instance, this instant in time, we can compare to the same instant in time on the position graph or even the acceleration graph. But this makes it very easy to see just by drawing a vertical line here, the same time on the other graph. So the slope of the position graph tells you the value of the velocity graph. For instance, if we were to actually measure this slope, let me see if I can extend this further out. That looks like about tangent. What we could do is, now that we've drawn in the tangent line, you could take any 2 points on the graph, or any 2 points on this line. For instance, it looks like this line passes through, there will be some good data points there. This looks like it's pretty close to 0.2, 0. Not exactly, but pretty close. So we can use that as an approximation. So 0.2, 0. Excuse me. And then maybe, would this work? That's pretty close, right? Maybe not exact, but if we just are rounding it off, that looks like about 0.8 and 1 meter. So this data point would be 0.8, 1. So if we calculate rise over run here, dy dt would be the change in y, y final minus y initial. So 0.8 minus 0.2 would be 0.6. And then we should probably mark the units here. That's 0.6 meters because it's a distance. No, shoot, that's time, isn't it? The y values are 1 and 0. So 1 meter minus 0 meters would be 1 meter. And then time, 0.8 seconds minus 0.2 seconds would be 0.6 seconds. So divide those, that's 1 over 3/5, so we get 5/3 meters per second. Or as a mixed number, 1 2/3 meters per second. So that would be the velocity at that instant in time. At this time, about 0.95 seconds, the velocity is 1 2/3. So at this instant, velocity is about 1 2/3 meters per second. The slope of the position graph at that instant tells you the value of the velocity graph at that instant. Any questions on that so far? So in general, if you're looking at one point at a time, you can use this approach to calculate the slope of a graph. And the slope of the position graph, or the slope of the tangent line of the position graph at that instant, tells you the value of the velocity at that instant. And you can do this at each point, a variety of different points on the position graph to get a variety of different values of velocity. But in this case, the velocity values are given, and those represent the slopes of the position graph at each instant in time. Some other ones I'd like to focus on. In particular, if you take a look at this location where, or this time, I should say, about 0.55 seconds. Right here. Make that thicker. Right here, what do you notice about the slope of the position graph there? Yeah, at that minimum, the slope of position is 0. And so at that same time, 0.55 seconds approximately, the value of velocity is 0. Because the velocity is the slope of the position graph. So at any max or min, if you have a time when the position reaches a max or min, the slope is going to be 0. And that means at that same time, the velocity value is 0. And note that that's in the middle of the bounce. The ball falls down, hits the ground, starts slowing down, comes to a stop, and then bounces back up. This instant in time is the turnaround point when it stops going down and is about to start going up. So the velocity stops being negative, passes through 0, and starts being positive. Negative velocity means the ball is on its way down. Positive velocity means the ball is on its way up. Any questions on that so far? And note that the velocity is changing throughout this entire process as well. We start with 0 velocity because we have 0 slope. The position graph is flat at this instant. And then as the position gets a steeper and steeper downward slope, velocity becomes more and more and more negative. If we focus on this tiny bit of time in the middle here, though, we suddenly stop getting steeper and start getting less steep, which means the velocity becomes less extreme negative. The position graph flattens out, has 0 slope for an instant, so the velocity graph passes through 0 as a value. And then the position starts to increase. We get a positive slope, so the velocity graph becomes positive. It reaches a maximum velocity as we get the steepest possible at the inflection point, 3. And then the slope starts becoming less and less steep. So velocity becomes less and less positive. The velocity is decreasing, but it's still positive. So a positive velocity means the position graph is increasing. Any questions on that so far? So let's see if we can use this to draw out the acceleration graph as well. And for the acceleration graph, we don't actually need the position graph. We can just draw the acceleration graph directly from the velocity graph, because how are acceleration and velocity related? What is acceleration defined as? Yeah, change in v over change in t. Or more formally, we should really call this a derivative also. Acceleration is the derivative of velocity with respect to time. It's not just the change in velocity divided by the change in time over some period of time. That will tell you the average acceleration, but the exact instantaneous acceleration at some instant in time is how quickly velocity is changing at that instant. Again, a tangent line. However, there are some values we can fill in here, I think, pretty quickly. Some of them would be values or instants in time where it's 0. One moment. Keeping track of positives and negatives, like whether it's in positive axis or negative axis. Magnitude is always positive, actually. Magnitude, in fact, I wouldn't even really say magnitude has a positive or negative sign. Magnitude is just absolute value. So magnitude is signless. If you need a sign, you could call magnitude positive, but I generally just think of magnitude as not having a positive or negative sign at all. For these graphs, though, the positive and negative are talking about whether it's in the positive, in this case, positive y direction or negative y direction, because we're talking about y component. So if the velocity is positive, that means the position value is increasing. If the velocity is negative, that means the position's value is decreasing. And same thing for acceleration and velocity. If acceleration is positive, that means the velocity is an increasing function. If the acceleration is negative, that means the velocity is a decreasing function. And I think we can split this up into regions here. Like if we take a look at velocity, starting from 0, it looks like velocity is a decreasing function, and it continues to be a decreasing function until when? At what time does velocity stop being a decreasing function? It starts at time 0. At what time does it stop being a decreasing function? Yeah, about 0.5 seconds. So from time 0 to time 0.5, that entire period of time, I guess a little bit further, that entire period of time, velocity is a decreasing function. In other words, it has negative slope. So what does that tell you about the value of acceleration? That doesn't actually tell us whether acceleration is increasing or decreasing, though. All it tells us is the sign, because acceleration is the slope of velocity. If velocity has a negative slope, then acceleration has a negative value. So the acceleration has to be a negative value during this period of time. If the velocity has a negative slope, then the acceleration has a negative value. Also, it looks like the velocity graph is a straight line during this time period. What does that tell you about its slope? What do you know about the slope of a straight line? It's constant, yeah. Velocity has a constant slope, so acceleration has a constant value. So that means the acceleration is a constant negative value during this time period. And we can even calculate what that is by calculating the slope of the velocity graph. We can do that by just taking any 2 points on it. Let's say 0, 0 is probably the easiest. And it looks like this is 0.5. And do we have a value there? looks like, I think these are in 2, so that's 2, 2.5, maybe 3, no, 4.5. Let's call that about 5. So that suggests it takes 0.5 seconds to accelerate to -5 meters per second. So if we calculate, and the reason we can do this, the reason we can just take the rise over run for this period of time is because it's a straight line. So we don't really need to draw in a tangent line because it's already a linear function. So for the slope of this line, we can say it's the change in y, sorry, change in v over change in t. Change in velocity is decreasing by 5, so that's about -5 meters per second. And the change in time would be 0.5 seconds. In other words, half a second. And I'm rounding this off a little bit here. It looks like it's a little bit different than 0.5 and a little bit different than 5, but pretty close. And what's 5 divided by 1/2? Yeah, 10. So -10 meters per second squared. So that means during this period of time, the value of acceleration is -10 meters per second squared. And that'll be a constant, so that'll just be a horizontal line on the graph. So let's graph that in. It looks like these tick marks, 1, 2, 3, 4, 5 make 100, so each tick mark would be 20. So -10 would be half a tick mark downwards. So our acceleration graph would be a flat line, half a tick mark downwards for that first time interval. And by the way, why -10 meters per second squared? Why does that look familiar? Yeah, this is the acceleration of gravity. Because that's the only force acting on the ball while it's in free fall. This first 0.5 seconds represents the time it takes for the ball to just fall towards the ground. During that period of time, acceleration is constant because it's experiencing gravity and that's it. That means the velocity is becoming more and more negative because gravity is pulling it downwards, making it get faster and faster in the downwards direction. And if you take a look at the position graph, what shape is the position graph during that first 0.5 seconds? What's that characteristic shape there? For the position graph specifically. So let's sketch this in. This shape. Yeah, that's a parabola. And the reason that's a parabola mathematically, going back to the acceleration graph, I would say the acceleration graph here is kind of the most fundamental or foundational of all of these. It's the last one we drew in just because of the information that was given. But what causes acceleration in general? What do you have to do to an object to make it accelerate? Yeah, you've got to apply a force. In this case, you've got an acceleration that's caused by a force, the force of gravity in particular. So if you know something about the force, you can usually draw the acceleration graph. And then from the acceleration graph, you take the integral and get the velocity graph. And then from velocity, you take the integral again and you get the position graph. If you've got a constant acceleration, which we do during this period of time, what's the integral of any constant? What do you get if you integrate a constant with respect to time? Well, what can you do with a constant inside an integral? Yeah, you can bring that out from the integral, and you just get a constant times integral dt. And what's integral dt? Well, it's already a 1 inside the integral. It's integral of 1 dt. Did they ever tell you in calculus class what the integral sign actually means? What that symbol stands for? Yeah, it's a summation. The integral sign is literally just a stylized S. I'm going to make this a big font because this is super important. No, actually, I need bigger than that. This should be like the biggest font I've got. That integral sign is literally just a stylized S, and it stands for summation. The integral sign literally just means you are adding a bunch of little pieces together. So this integral sign means the summation of, and then dt means a tiny piece of time. If you have a bunch of tiny bits of time and you add them together, what do you get? If you take this tiny bit of time plus 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 this tiny bit of time, add together all the tiny bits of time, and that adds up to what do you get if you split something into a bunch of little pieces and then add all those pieces together? Yeah, you just get the amount of time. So the integral dt is literally just t. That all that means is that the integral dt is t. All this means is if you add up all the tiny bits of time, you get the total amount of time. Formally, that should be change in time because it's the total amount of time that has passed. It's not like it's the amount of time since the beginning of the universe or something. But all this means is if you add together all the tiny bits of time, you get the total amount of time. Or we sometimes write this as t plus a constant. The idea being that that constant represents the effect of the starting time. But this is where this comes from. Integral dt is t plus a constant because you're literally just adding up all the tiny bits of time to get the total amount of time that has passed. So that means, and let me fill in that constant. That constant is acceleration. So this becomes acceleration times time plus a constant. And that constant, it turns out, represents the starting velocity, because if you plug in 0 for t, you just get c equals v at time 0. So that's v initial, or v0. And what would you get if you graph that? If you graph v equals a constant times t plus a constant, what shape does that create? If you just graph a constant times the input plus another constant, what shape does that create on a graph? Yeah, that'll be a straight line with this constant a as the slope and this constant v naught as the intercept. So the velocity will be a straight line. In general, anytime the acceleration is constant, that tells you the velocity is going to be a linear function. And we could also take this a step further. We could integrate that linear function. The position is going to be the integral of velocity. If we fill in at plus v naught as the velocity, we could integrate that as well. And we could split that up. We could split it up into acceleration, because a constant can be pulled out, times the integral of time dt plus integral, or plus v naught times integral of 1 dt. And anyone remember what the integral of t dt is going to be? If you take t to the first power and integrate, what happens to it? It might help to write this. Yeah, it's going to be t squared, right? Because if we want to integrate t to the first power dt, this is the opposite of taking a derivative. When you take the derivative, you decrease the exponent. So we need a higher exponent when we integrate, t squared. The problem is, if you just take the derivative of t squared, what would you get? You get 2t, yeah. We don't want 2t though, we just want 1t. So we need an extra divided by 2 to cancel that out. So the integral of t would be t squared divided by 2. The divided by 2 balances out the times 2 we would get from the derivative of t squared. So that means the integral of t dt, that whole thing is t squared over 2. So acceleration times t squared over 2. And then we already saw that integral dt is just t itself. And then also plus a constant, which turns out to just be the starting position. In other words, something t squared plus something t plus something. What would that graph look like if it's got a t squared in it? Yeah, that'll be a parabola. It's a quadratic function, so the graph will be a parabola. So in general, in any situation where the acceleration is constant, just a flat line, then you know the velocity will be a diagonal line with the acceleration as the slope, and the position graph will be a parabola with the acceleration determining how tightly curving it is. The velocity determining the initial slope, or the starting velocity determining the initial slope, and the starting position determining the initial value. So that's an important thing to keep in mind. In any situation where the acceleration is constant, you can know in advance that the velocity will be a straight line and the position will be a parabola. And that also goes in reverse. If the position is a parabola, then the velocity is a straight line and the acceleration is constant. Any questions on that so far? Also in this situation, is there any other period of time where we know that the acceleration will be a constant? Specifically that same constant. Is there any other period of time where it's in free fall? Yeah, it looks like from about 0.6 to 1.2 and possibly beyond, but we only have the graph up to there. From here onwards, it's also a straight line. Or that is, the velocity graph is a straight line with the same slope. It's still it's in free fall. So before it hits the ground and after it leaves the ground, the ball is in free fall. So that's going to continue to be that same slope of -10, because it's got the velocity has the same downward slope, so the acceleration is that same negative value. So during those two entire periods of time, the acceleration is a negative value, specifically -10, which means we really just need to focus then on what's going on in between. In this section between those times, what does that short period of time represent? What's going on during that little tiny bit of time? Yeah, that's the bouncing process itself. That's the period of time where it's when it's in contact with the ground. And so during that period of time, what do you notice about the velocity during that short period of time? Yeah, it's increasing. And an increasing velocity tells you the acceleration is what sort of value? Yeah, well, not increasing. I would say the acceleration is positive. The velocity is increasing, so the acceleration is positive. So during this short period of time, the velocity is increasing. In other words, it has positive slope. So during this short period of time, the acceleration is positive. The velocity is an increasing value, therefore a positive slope. So the acceleration has a positive value because the slope of velocity tells you the value of acceleration. And the velocity, it looks like it's not quite a straight line during this period of time, but I think we can probably approximate it as a straight line. If you approximate the velocity as close to a straight line during this period of time, let's say from here to here, it's not exactly a straight line, but I think that'll be a good approximation to get at least an average slope and therefore an average acceleration. So during that period of time, we have, we started at a velocity of, I think that was about -5. And then we're going to a final velocity of, I think that's supposed to be +5 based on the tick marks on the graph. So what's the change in velocity during that short period of time? Yeah. It can't be 0 because even though it's the same speed, we are changing velocity because we're changing direction. We're going from 5 meters per second downwards to 5 meters per second upwards. So that's actually a very large change. In fact, you can see this as final minus initial, +5 minus -5, that's 5 plus 5. So that's 10, +10 meters per second, exactly. So we're changing velocity by 10 meters per second over the course of how much time? What is that short period of time there, approximately? Yeah, it looks like about 0.1 seconds, about 1/10 of a second. So to find the average acceleration, and keep in mind this is average acceleration. This isn't truly the acceleration at each instant. This is just the average acceleration. But if you divide those, 10 divided by 1/10, what would you get? Yeah, that'll be 100 meters per second squared. So that means during this period of time, the average acceleration is 100. That doesn't mean it's 100 the whole time. But if we approximate this as a straight line, that's about 100. So during this period of time, acceleration on average is 100. So the acceleration is -10 for a while because of gravity. And then during the impact, we get this sudden spike. Acceleration jumps up to 100 and then back down to -10. And again, this is an approximation. Realistically, it's not just suddenly kicking into 100 and then suddenly dropping down to -10. Realistically, it's going to be more of a gradual transition because as soon as the basketball hits the ground, you're gradually changing the force as the basketball compresses and then gradually changing it again as it stretches out. So realistically, I would expect this to be more something like this. A rapid but not instantaneous change, increase, and then a rapid but not instantaneous decrease. The flat line at 100 is just an approximation. Realistically, it's less than that some of the time, more than that some of the time. In fact, if you take a close look at the velocity graph, we approximate it as being this steep the whole time. Realistically, it's less steep some of the time, more steep some of the time, and then less steep some of the time. So the actual acceleration should be less than 100 some of the time, and then goes up to more than 100, then dips back down to less than 100. But it averages out to 100 during that short period of time. Any questions on that so far? And this problem was also asking about drawing force diagrams for these instants in time. And I think there's really only a few points we need to care about. For instance, let's say during the free fall portion, before the ball hits the ground. So basically anytime between 0 and 0.5 or anytime between 0.6 and 1. During that period of time, what forces are acting on the ball? Yeah, we've got gravity from 0 to 0.5 seconds. So the first half second of time. We've got gravity pulling down. Do we have anything else? Friction would be if it's sliding on some surface, but it's not sliding on some surface. It's just in free fall. You could possibly have air resistance, but I think we're assuming here that air resistance is small enough we can ignore it. Yeah, I'd call it just gravity here. Air resistance could play a role, but I don't think the ball is really going fast enough that air resistance would play a major role here, especially since we found that the acceleration is about -10 meters per second squared, which is what we'd expect from just gravity. So during those that first half second, we've got force of gravity, m times g, and nothing else. So that's the entire force diagram while it's in free fall. In fact, that's technically the definition of free fall. Free fall means a situation where gravity is the only force acting on the object. And the same is true after it bounces off the ground. For the last half second, when it's on its way back up, during that period of time, it's also in free fall. Even though it's on its way up, that's still called free fall because gravity is the only force acting on it. So this would be the force diagram for the first half second before the bounce, and the last, let's say, 0.4 of a second after the bounce. During the bounce, though, things get tricky because during the bounce, what other force is involved here? Yeah, we'd have a normal force because as soon as the ball becomes in contact with the ground is now exerting a normal force upwards on the ball. And how much normal force actually changes as time passes? At the very beginning, let me move this down. I think we're going to need some more space here. At the very beginning, we have a normal force, like as soon as it hits the ground, we get a normal force. But that normal force is very weak because the ball and the ground are not interacting very strongly yet. So as soon as it hits the ground, we get a weak normal force, which means it's still accelerating downward. But as the ball gets more and more compressed, what would you expect to happen to the normal force? 0.2 is actually further along the road. I would say like more as soon as it impacts the ground. At location 2, though, what do you notice about the acceleration at time 2? At that time, what do you notice about the acceleration? Yeah, the acceleration has increased to specifically a very large positive value. If the acceleration, yeah, we're going to need a higher normal force. The normal force actually changes depending on how hard the ball is mashed into the ground at this instant. So if the ball has just barely touched down, there's very little normal force. But as the ball gets more and more smashed as it goes further down, the normal force gets stronger and stronger and stronger. Yeah, we only experience a normal force if these surfaces are actually in contact with each other. As soon as, or before the ball hits the ground, there's no normal force. While the ball's in contact with the ground, there is a normal force. But then as soon as the ball leaves the ground, there's no more normal force. So 2 and 3 on this graph will be the only marked instants in time that have a normal force at all. At instant 2, at time 2, it looks like the normal force is or the acceleration is very large positive. So we actually need a very strong normal force at instant 2, because at instant 2, the forces have to add up to a large upward force. A strong positive acceleration means a strong upwards total force. So the normal force needs to be much stronger than gravity, not only enough to cancel out gravity, but enough to have lots of extra upwards force left over to make the total acceleration upwards. In fact, if the acceleration is upwards and more than 10 times as strong as gravity, the normal force is actually going to have to be more than 10 times stronger than the force of gravity. So to draw this more to scale, I should actually be drawing gravity much weaker. Normal force is going to be over 10 times as strong as gravity here. In fact, more than 11 times as strong as gravity, because it needs to cancel out gravity and have 10 times as much left over. So during the impact, especially midway through the impact, when the basketball is compressed at its most, we're going to have a lot of normal force. In fact, you could think of the basketball as acting very much like a spring here. A spring gives you the most force when it is most compressed. Same thing with the basketball. When the basketball is most compressed, it's got the strongest force involved. The normal force here is acting very much like a spring force. At point 3, though, point 3 is after the ball has started to rebound back up. It's still in contact with the ground. It's just about to leave the ground, in fact. In fact, at point 3, it looks like, let's zoom in on that point. Or let's focus on that point. At that instant in time, time 3, it looks like at that instant, what's the acceleration, or what's the slope of the velocity graph at that instant? I guess that should be a little further to the right. At that instant in time, what's the slope of the velocity graph? Yeah, it looks like 0. It looks like the velocity graph has reached a maximum. We've got the maximum velocity, meaning the slope is 0, meaning 0 acceleration. At that instant, at time 3, the acceleration is 0. What does that tell you about the force? Total force is 0, yeah. And what's the only way for the total force to be 0 here? Yeah, the forces have to cancel out. And of course, we can't get rid of the force of gravity. The force of gravity is always going to be there. But what do we have to know about the normal force in order for them to actually add up to 0? The normal force would have to be what? Yeah, or at least same magnitude and opposite direction. So at that instant in time, and yeah, I would say equal magnitude, but opposite direction. So at instant 3, the fact that the acceleration appears to be 0 means the forces have to be canceling each other out. So the normal force has to have the same magnitude as the force of gravity. Time 3 is the instant when the normal force, we're at a level of compression where the normal force happens to be the same strength as the force of gravity, the weight of the basketball. And that's also interesting from a mathematical perspective. At that instant, that's the instant when acceleration happens to be 0. So velocity reaches a minimum or a maximum, in this case, a maximum. And what would we call that point on the position graph? If the velocity has stopped increasing and started decreasing, or where the second derivative has stopped being positive and started being negative. Terminal velocity is something different. Terminal velocity is more when air resistance balances out the force of gravity, but we're assuming no air resistance here. But think back to calculus. we're looking at an instant where acceleration, which is the second derivative is 0. If you're setting the second derivative equal to 0, what are you searching for? What kind of point are you looking for there? That's an inflection point, exactly. When the second derivative is 0, when in this case, the acceleration is switched from positive to negative, that means the velocity has switched from increasing to decreasing, which means the position graph has switched from having a slope that is increasing to having a slope that is decreasing. We're changing concavity, concave up to concave down, because the value of the sign of the second derivative being positive or negative, tells you whether the function itself is concave up or concave down. So all those ideas from calculus, the idea of slope, concavity, curvature for first and second derivatives, all of that still applies here. Velocity is the second derivative, so it tells you about the slope of the position graph. Acceleration is velocity is first derivative, so it tells you about the slope. Acceleration is the second derivative, so it tells you about the concavity and curvature of the position graph. Acceleration being positive means the position graph is concave up. Acceleration being negative means the position graph is concave down. So all those ideas from calculus still apply. We're just adding specific physical meaning to the variables. And you might find it useful to go back to any notes or textbooks you have from calculus. Take a look at all of the facts and theorems and ideas about derivatives and integrals, but look at them from the framework of assume that the original graph is time versus position. Most of the important facts from calculus make so much more sense if you're looking at a time versus position graph. And that's largely because this is what calculus was invented for in the first place, dealing with graphs of time versus position, keeping track of moving objects. Any other questions on that? You're welcome. I will see you next time.